Hey everyone, welcome. You know all that stuff you learn in science class? Ever wonder if it can actually build something real, something that actually matters? Well, today we're going to dive into this amazing project that does exactly that. We're talking about turning textbook knowledge from biology, physics, and geology into a real blueprint for a sustainable, climate-proof home. It's pretty cool. So let's jump right in.
All right, let's kick things off with a bit of a puzzle. What in the world could a tiny, single plant cell possibly have in common with a full-sized, climate-proof house? I mean, really? The answer, it turns out, is, well, pretty much everything. And once you see that connection, it completely changes how you look at science and engineering for real.
Okay, so first things first, let's set the scene and really understand the challenge here. Because this isn't just some abstract idea. This is a real mission with some serious stakes. So the goal is pretty ambitious. You have to design and build a home that can handle a really harsh climate. Think of a scorching hot desert. And here's the kicker. You can only use natural materials that you find right there, locally. So we're talking about a house that's not just strong, but one that actually works with the environment to keep people safe inside. You can see how this ties directly into huge global issues, right? Like sustainable living and how we're going to adapt to a changing climate. So where do you even start with a challenge like that? Well, the answer, believe it or not, starts super, super small. We're going to look at nature's own tiny blueprints for that first big idea. And here's the core idea. A eukaryotic cell is, no joke, a total masterpiece of design. Think about it. It's got all these specialized parts, protective layers, a whole system for energy. It's this tiny, self-regulating, perfectly protected little fortress. Which, hey, that sounds like a brilliant blueprint for a building, doesn't it?
And what's so cool is how direct these comparisons are. Okay, check this out. The cell membrane, the part that controls what comes in and out, that's basically our house's walls managing heat and air. The nucleus, with all the DNA and instructions, that's our architectural blueprint. The mitochondria, the powerhouses of the cell, that's our model for an efficient energy system. And the plant cell's strong, rigid wall, well, that's our structural support, giving the house all its strength, using those same kinds of plant-based fibers.
All right, so we've got our blueprint, inspired by biology. Awesome. But what are we going to build this thing with? Now we have to shift gears and think like a geologist. Go out, find our materials, and put them to the test. Yeah, forget steel and concrete. We're looking for stuff like rice straw, cotton stalks, sugarcane leftovers, palm fibers, things people usually just see as agricultural waste. And this is where geology becomes so important. It gives us the tools, the scientific methods to really understand these natural materials and figure out if they've got what it takes. And this is how we make the call. We're not just guessing here. We are testing and comparing these materials scientifically, almost exactly like a geologist would identify different rocks or minerals. We're measuring things like their density, how well they hold up under pressure, that's the static load, and of course, how they handle fire. All that data is what tells us which material, or maybe which mix of materials, is going to be the winner for our specific climate. Let's just focus on one of those for a second: density. Why is that such a big deal? Well, in construction, materials with low density, like that rice straw, are full of tiny little air pockets. And those air pockets are just awful at transferring heat, which makes them amazing insulators. It's literally the same reason your puffy winter jacket keeps you warm. It's just trapping air. And that simple scientific idea is the secret to keeping the house cool without cranking up an AC.
Okay, so we've got our design and we've picked our materials. We're on a roll. But now comes the next big hurdle. We have to deal with all the invisible forces that are going to be pushing and pulling on this house 24/7. I'm talking about gravity, the sheer weight of the roof, the force of the wind.
I'm sure we've all heard this one from Isaac Newton, right? For every action, there is an equal and opposite reaction. Well, when you're building something, that's not just a cool quote for a physics textbook. It's the absolute fundamental rule for making sure your building doesn't fall down. A stable building is all about balanced forces. Every single push has to be met with an equal and opposite push back. So there's a technical name for this state of perfect balance. It's called static equilibrium. And all that really means is that when you add up all the forces acting on the house, the pushes up, the pulls down, the shoves from the side, they all cancel each other out. The total is zero. So the downward pull of gravity gets perfectly matched by the upward push from the foundation. The sideways force of the wind is met with equal strength. the building doesn't move. It's like every force is in a perfect standoff. And that, right there, is the goal. Okay, so how do you actually make sure you've achieved this perfect balance? Well, engineers have this really simple but incredibly powerful tool called a free body diagram. All you do is you take one single piece of the building, like, say, a roof beam, and you draw arrows to represent every single force that's acting on it. It creates this little visual map, and from that, you can literally calculate if the forces are all canceling out. It's how you prove, mathematically, that that part of the building isn't going anywhere. So we've hit biology, geology, and physics. Now it's time to bring in the big guns, math and computer science. These are the tools that are going to let us translate all these physical principles into an actual, concrete plan for the building. Okay, I know what you might be thinking. Trigonometry. All that sine, cosine, triangle stuff from high school, right? But here, it's not just abstract math. It's an incredibly practical design tool. We use those very functions to figure out the absolute perfect angle for the roof. You want it steep enough for rain to just slide right off, but also angled just right so it deflects the sun's heat during the hottest part of the day. See? Practical. And of course, math is the language we use to understand our data. After testing all those materials, we don't have to just guess which one is strongest. We have hard numbers. And when you visualize that data, like in a simple bar chart, the winner becomes obvious. You can see it right here. The cotton stock mix, hands down, had the best compressive strength in these tests. You know, it's not just about raw strength. Consistency is absolutely key. And that's where another math concept comes in, standard deviation. All that means is it's a measure of how consistent your test results are. If you get a low standard deviation, it means the material performed pretty much the same way every single time. And for an engineer, that is music to your ears. It means the material is predictable, it's reliable, you know exactly what you're working with. And finally, we bring in computer science to pull it all together. We use 3D modeling software to build a complete virtual prototype of the house. We can test the design, see how the sun will hit it throughout the day, make sure every single piece fits together perfectly. And we do all of this before a single brick is laid. Saves a ton of time and money. So that brings us to the big takeaway. We've kind of gone on a journey here, right? Through biology, geology, physics, math, computer science. Now let's wrap it all up and see what it really means. Here's the most important part of this whole thing. The true product here isn't just a house. It's actually a new way of thinking. It's learning how to look at a really complex problem and then pull in ideas from totally different areas of science to come up with a solution that actually works. It's about seeing that hidden connection between a living cell, a chunk of earth, and a finished building. I want to share this one quote from the source material that just nails it. It says, understanding x, v, and a, the classic physics variables for position, velocity, and acceleration, means understanding how your structure breathes, bends, and survives in a changing world. I mean, how cool is that? It just perfectly shows how even the most basic physics isn't just letters in a formula. It's the language we use to describe how a building is alive, how it fights back against nature to survive. So, I'll leave you with this to think about. If a project like this can draw a straight line from a microscopic cell to a full-blown sustainable house, what other amazing hidden connections are out there, just waiting for you to find them? Thanks for joining us for this explainer.